Okay, welcome to Wednesday, November 4. This is our class session, and we have been working on identities this week and in the week before we took the tests. So we're just nearly finishing that up now. There might be some other identities in the future that we're going to look at, but after today, we've handled almost all of the major identities. I'll remind you of this on our formula sheet. Get a couple more people in the room. Find where I have my highlighters. It looks like the yellow highlighter works a little bit better on the camera than the green one. So this is the formula sheet we've been using throughout the class. And most recently, we've done the double angle identities and the half angle identities. We've crossed out identities as we go. On the back side, we still have identities in our future, the law of sines, law of cosines, and then some other special identities based on the complex numbers. But today we'll talk about the sum to product and product to sum identities. These identities are identities that you generally reference from the formulas, so you have to know how to use the formulas, but they get their names because they do exactly what they say. A product to sum identity takes a product of two cosine waves or two sine waves or a sine wave and a cosine wave and rewrites it as a sum or a difference of two cosine waves or two sine waves. And you can also run that in reverse. If someone gave you a sum of two sine waves and you wanted to know what it looks like, it's kind of very interesting. You can think of it as a product of a sine wave and a cosine wave, or a cosine wave and a sine wave, or a cosine wave and a cosine wave. Any variation, a sine wave and a sine wave. And the part that you have to get correct is how the quantities of the angles change. But it makes a very interesting visual pictures. And so this is something we can demonstrate on Desmos. So these are the last identities we're doing in this week. But just to remind you about how all these identities go together. So we've discussed double angle identities, half angle identities, and today we'll finish the sum to product and product to sum identities. But just to remind you how all these angle identities go together and their purpose, think about this key principle that we tried to state last time. That once you uniquely describe an angle, then our identities allow us to calculate everything about that angle, not just the 6 trig values of that angle, but the 6 trig values of the double angle, the 6 trig values of the half angle. So part of the purpose that we have today is to show you, prepare you, that if I described any angle to you and picked out any one of these function values, single angle, double angle, half angle, then you could name those just by making the appropriate drawing and using the appropriate identity. And this also involves angles that you describe from inverse trigonometric functions. So you can't forget what the inverse trigonometric functions do to describe an angle for you. And we'll give you some examples like that. So this is the key principle that you have to believe. In fact, once you have the sine of double angle, then you could have the sine of 4 times the angle just by doubling the double angle. You could have the sine of 3 times the angle just by adding the angle and the double angle. So what we've really discovered is to describe any sine or cosine value related to an angle, all we need is the sine and cosine values of that angle. Remember, sine and cosine values themselves determine tangent, cosecant, secant, and cotangent. So everything comes down to those two values. So you have a very straightforward procedure for accomplishing this mission. First, you draw the angle that someone's describing to you in the appropriate quadrant. First quadrant, second quadrant, third, fourth quadrant. Next, add a drawing of the reference triangle and label the reference triangle, both the legs and the hypotenuse, with positive numbers. Think about the reference triangle as a physical triangle where you're measuring the two legs and the hypotenuse. You always measure lengths with positive numbers. Third, locate and label a point on the terminal side of the angle theta. And that you do by including the correct signs for the x and y coordinates. And those signs are based on the quadrant where the angle terminates. Now, if you have a quadrantal angle, that's a multiple of 90 degrees, plus or minus 90 degrees, then you really don't draw a reference triangle because the reference triangle is either 0 height or 0 width. And so you have to know the sines and cosines of the quadrantal angles of any multiple of 90 individually. But those are the points on the unit circle, where the unit circle intercepts the x and y axis. Plus and minus 1 and 0, those are the sine and cosine values for any quadrantal angle. After that, you apply the appropriate identity. So let's give it a spin. This dark line paper is not showing up excellently on the camera right now. So let me find another pad of paper. And let me switch that. Okay. We'll just go through that procedure. And this is the same procedure that's outlined in the book. And you can use the video recording to make your own notes of it if you like. But let's say that I told you that the cosine of theta was minus 3/7, and that theta was in quadrant 3. Now that's enough information to draw one and only one angle between 0 and 360 degrees. Now, we had a long list of functions, right? So what if I just pick some random values off of here? Let's take the cosecant of theta, the tangent of 2 theta, the secant of 1/2 theta. Let's try it. Cosecant of theta the tangent of 2 theta and the secant of 1/2 theta. But really, think about every trigonometric function value. Once you know the angle, you can name all 6 values of theta. You can also then name all 6 values of the double angle, all 6 values of the half angle. But if I just pick one out for a spot check, then you have to provide that particular value. Okay, so procedure. Let's draw the angle. Doesn't have to be a perfect drawing, but make it a fair drawing. Cosine is -3/7, and theta is in quadrant 3. Now the cosine is the x value over the r value. So this x value is a little bit less than half of the radius. So let me try to draw something that looks like it's following that. Let's pretend this radius is 7. And let's pretend at this point right here, you know, the x and y is -3. And I don't know what the y is yet. Let me label this side the reference triangle with positive values. So even though this point is -3 on the x-axis, the length of this side is 3. And that allows me to find the length of this side. So I use the Pythagorean theorem and I say 3 squared plus y squared equals 7 squared. So 9 plus y squared equals 49. Y squared is equal to 40. And so now y is plus or minus the square root of 40. I got to do 2 things. I want to simplify this as much as possible. And the biggest perfect square inside there is 4. So we have to select plus or minus 2 root 10. I select minus 2 root 10 because I'm in the 3rd quadrant and the y coordinate has to be negative. But I label this side. How long is this side? I'm going to label it 2 root 10 units long. Okay, now I can work out all of these functions. What's the cosecant of theta? Well, it's 1 over the sine of theta. And the sine of theta is y over r. So y is minus 2 root 10. R is 7. So to divide by the fraction, I invert and multiply. And I get minus 7 over 2 root 10. That's the cosecant of theta. I could also say sine of theta is minus 2 root 10 over 7. I could just think about that ratio and say instead the cosecant of theta is 7 over minus 2 root 10. I use the minus sign because I'm in the 3rd quadrant. So I express it like this. Let's go for tan of 2 theta. For the tangent of 2 theta, I need this identity off my formula sheet. 2 tan theta, 1 minus tan squared theta. In order to do this, I need to know what the tangent of theta is. And the tangent of theta is y over x. Never forget your original descriptions of the trigonometric functions. And that's one reason why you should have them memorized, because you don't have time to always flip back and forth between your papers or windows. So y divided by x is minus 2 root 10 divided by minus 3. The two minus signs cancel out. So the tangent of this angle, I'm going to need to write it down here, is 2 root 10 over 3. Now I insert those in this place right here. 2 times 2 root 10 over 3 divided by 1 minus 2 root 10 over 3 squared. Now let's not do rationalizing denominator. I don't have any problem with you leaving the radical in the denominator if they don't specify otherwise. But I can't leave fractions inside fractions. This is kind of messy. So let's clean this up a bit. So up on the top, I got 4 root 10 divided by 3. On the bottom, I have 9 over 9. That's 1. Plus 2 root 10 squared over 9. Or minus 2 root 10 squared over 9. And 2 root 10 squared is 40. Square the 2, square the root 10. 4 times 10. So what does this turn into? It's not hard to track if you just do everything one step at a time. Minus 31 over 9 is on the bottom. And so you invert and multiply again. 4 root 10 over 3 times minus 9 over 31. There's very little canceling here. I get to cancel between the 9 and the 3. I guess I could say 9 is to 3 as 3 is to 1. I guess I could cancel one factor of 3 right there. But when I multiply these out, what do I have? Negative 3 times 4, negative 12 root 10, divided by 1 times 31. I was doing good with my paper raising. Then I just ran out of space. So this is the value of the tangent. Now, I'm a little bit nervous right here because tangent in that quadrant should be positive, right? In the first and third quadrants, tangent of angle should be positive. But then I remember I'm not talking about this angle, theta. This angle theta does have a positive tangent. I'm talking about double theta. And so if I double theta, I must be landing well over in this second quadrant. So the negative sign here doesn't bother me. In the second quadrant, angle has negative tangent. Okay, one more. Secant of 1/2 theta. So we have to make a choice here too. And I think I'm going to write it over here on the left side. I'm going to use my half angle formula. But first of all, to know secant of half theta, I'm going to calculate. I don't have a formula for secant of half theta. I have a formula for cosine of 1/2 theta. So I'm going to take cosine of 1/2 theta and turn it upside down, flip it over. So I need to know the cosine of 1/2 theta. By the formula, our half angle formula, I have to choose plus or minus 1 plus cosine theta over 2. In this problem, the cosine of theta was given to me outright at the beginning, minus 3/7. I can read it from my drawing. X is minus 3 over r equals 7. So I have 1 plus negative 3/7 divided by 2. Then I square root, then I choose plus or minus. Now, 7/7 minus 3/7 is 4/7. And 4/7 divided by 2 is 2/7. I'm not crazy about having a whole fraction inside there. Maybe we'll consider adjusting this in a second. But first I have to decide, is it plus or minus? Now let's think about this. The angle theta is over here between 180 and 270. So where is 1/2 of theta? If theta is pinched between these two lines, then half theta will be between half of 180 and half of 270. Half of 180 is 90. And half of 270 is 135, which is over here. So 1/2 theta must be somewhere between 90 and 135. Now, I don't know exactly where. I could ask the calculator to invert one of these values, but let's just say it's about here. Approximately. So you decide the cosine of an angle in the second quadrant. What is that? It is negative. So now I have the cosine of 1/2 theta is negative root 2 over 7. So now I can work out the secant. I just take the reciprocal of the cosine, negative root 7 over root 2. I can split the root up into two separate roots. I'm not always one for rationalizing denominators, but it's always awkward to have two radicals in the same picture, the same problem. Why don't you just have one? So let's multiply by root 2 and root 2. So you could express this as minus root 14 over 2. So any time someone specifies single angle, double angle, half angle of any one of the 6 trigonometric functions, you're able to calculate it, and you must be able to calculate it just from your identities and the standard values of the original angle. This is really, really hard to emphasize enough. This would be like a key component of the course. Excuse me, I gotta bring someone in there. So I want you to be prepared for this. You might see this more often on future homework or future exam. At the drop of the hat, if someone describes an angle to you and picks any one of these values out, you have to be able to provide it. Okay, let's try another one, and let's use the inverse trigonometric functions. So another example. Let me keep my pages numbered here. Let me move that out of the way. And let's say that I asked you for this. What is the sine of 2 times the tan inverse of negative 1/4? That looks like a mouthful. Sine of 2 times the tangent inverse of minus 1/4. How do you resolve this? So you have to remember that this tan inverse right here, the inverse trigonometric functions describe a specific angle to you. So this is some angle theta that someone wants you to draw. And then they want you to evaluate the sine of 2 times theta. Now you have a formula for the sine of 2 times theta, just as long as you could draw theta correctly, right? So how do we draw tan inverse of minus 1/4 correctly? When someone says theta is tan inverse of minus 1/4, what are they saying in English? Theta is the angle whose tangent is minus 1/4. Practice saying inverse functions exactly like that. Cosine inverse, secant inverse, tan inverse, cotangent inverse, whatever inverse function. When someone describes a function, an angle to you with an inverse trig function, then they're saying that this is the angle whose tangent is minus 1/4. And from that, I can draw the angle and find the value that they ask of me. Okay, so x and y axes. Tangent is minus 1/4. Where is the tangent negative? Where do we choose tan inverse from our identities? Tan inverse is chosen between minus 90 and 90. So angles in the first quadrant have a positive tangent. Angles in the fourth quadrant have a negative tangent. Since I want a tangent of negative 1/4, I need to be going into the fourth quadrant. Also, the tangent is the y value over the x value. So I want an x value that's relatively large, 4-ish, compared to the y value of 1. The y value is going to be negative. So I'm going to draw a triangle with an x to y ratio of approximately 4:1. You don't have to draw these exactly accurate, but it helps if you draw them fairly accurate. It helps you not confuse yourself. Here's my reference triangle. There's my point. Y over x is minus 1/4. And this makes this side 4 units long. And I'm thinking about the reference triangle, just length 1 unit long. Don't call it minus 1 unit long. Reserve that minus sign for the point, xy. So this is the angle that they're describing to us. It's a negative angle. Don't spin all the way around because you have to select this between minus 90 and 90. But I don't have to name that angle to find the sine of 2 times that angle. So let's call this theta. Now I go for the sine of 2 theta. So the formula for that is 2 sine theta cos theta. I have to know that identity. And now I have to read the sine and cosine off this triangle. That means I'm going to need the hypotenuse length. So I'll use the Pythagorean theorem. 4 squared plus 1 squared is 16 plus 1, that's 17. So the R right here is root 17. That hypotenuse is root 17 units long. I'm writing a little too small. I apologize. I squeezed it into the bottom of the paper. I'll try to write larger next example. But now I can read the sine and cosine. Sine is y over r, negative 1 over 17 root. Cosine is x over r, 4 over 17 root. And then I double that. I still have to finish this off by correctly simplifying, but multiply these 3 fractions. 2 over 1 is a fraction. 2 is equal to 2 over 1. So I have minus 8 on the top, and root 17 times root 17 is 17 on the bottom. So that's what the sine of 2 times the tan inverse of minus 1/4 is. Now, I'm just kind of curious if I can verify that with a calculator. And I could get really good response from my calculator, or I just could get an acceptable response from my calculator. So let's try it. And don't need the drawing anymore. I'll cover up the drawing. But let's talk about, am I in radians or degrees? Well, I'm never going to see the actual angle, so I don't mind which one I'm in. I'm kind of curious, since this is such a small angle, I'd like to see the degrees. Is it, I don't know, minus 10, something like that? So let's first just ask the calculator in degree mode, what's the tan inverse of minus 1/4? Okay, it's minus 14 degrees approximately. But I didn't need to know that to check this answer. I could type in directly sine of 2 times the tan inverse of minus 1/4 in the parentheses. And I get this number. Now, the problem is I have to match that to the minus 8/17. I think it does match, but there's 2 ways to do it. First of all, I could just type in minus 8/17, see if I get the same number. Remember on the math key, though, you can sometimes ask the calculator to turn it into a fraction. Can the calculator turn this number into the correct fraction? I'm just curious. It does recognize it as minus 8/17. So I want to be really careful with you for your next exam and homeworks and things like that. You see clearly that I just type this in and I get minus 8/17. So when you write the question on the exam or homework, if you just write the answer minus 8/17, I'll literally give you 0 points. The question's going to say, show me how to do this. And that means you're going to draw the angle, correctly label everything, use the correct identity, and simplify it correctly. So I'm not interested in whether your calculator knows how to do this. I already know the calculator knows how to do this. I want you to be able to demonstrate this technique. So it's absolutely acceptable for you to use your calculator to check, but just make sure that you know how to do this yourself by hand. Now, I could also work out the cosine of 2 theta. And then I could work out all the other 6 values. Why don't we try that? What's the cosine of twice theta? Well, according to my identities. And I have 3 choices for cosine of 2 theta, right? I'll take the first one. Cos squared theta minus sine squared theta. And I already worked out the sine and cosine theta right here. So squaring cosine give me 16 over 17. Squaring sine gives me 1 over 17. And subtracting them gives me positive 15 over 17. I could even draw that angle possibly, right? It's an angle with a negative sine and a positive cosine, and it's this tiny negative angle doubled. Well, that would just be still in the 4th quadrant, just a little bit slighter down. It would have a negative sine and a positive cosine. So I feel very good about that. But what if someone really challenged us and said, okay, I'm going to bring this paper down a little bit. You've done the sine of 2 theta. You've done the cosine of 2 theta. Give me all the other ones. Tangent 2 theta, cosecant 2 theta, secant 2 theta, cotangent 2 theta. Well, you understand that everything's made out of sine and cosine. So if you know these 2, you know all the others. Here's the minus 8 over 17. And here's a 15 over 17. Immediately, you fill in the cosecant and the secant. Minus 17 over 8. 17 over 15. Then by dividing sine and cosine, you fill in the tangent. Divide minus 8 17ths by 15 17ths, and you get minus 8 over 15. You invert and multiply, and the 17s cancel. Cotangent is the reciprocal of tangent. So this will be minus 15 over 8. So whether someone asks you for one of them or all 6 of them, it's not much different work. That's the point that I'm trying to make to you right now. The amount of work is not much different. All I had to do was determine the sine and cosine, and then flip, flip, divide, flip. Once you realize that about the 6 trigonometric values, that if you know 2, you know all, then you're in a very, very strong position. Okay, let's do one more before we do the sum to product and product to sum identities. What if I asked you, I can't think of, let's try to really jazz it up. One of our identities. What if I said, what is, okay, and I'm gonna definitely challenge you on this one. So this is definitely a challenge one. Cotangent of secant inverse of minus 3 over root 10 plus sine inverse of 1/5. I have no idea what this is going to turn into. On the other hand, I can check it with my calculator after I'm done. So what do we have to do? We have to draw these two angles. Let's call this angle A. Let's call this angle B. Right now I'm coming up with a game plan. Then I need the cotangent of A plus B. I don't have a formula for cotangent of A plus B. Oh, but I do have a formula for the tangent of A plus B. So once I draw these two angles, I can use the formula for the tangent of A plus B, and then I'll take the reciprocal to get the cotangent. That's our plan. Now, a tip is to draw these angles separately so that your drawing doesn't get too cluttered and messy. So I'm going to draw these two angles separately. And then I'm going to draw the angle A plus B on the third graph here, because this is most like the homework questions I'm asking you right now, to draw all the angles that we describe. Okay, what is the angle I have to be careful with my secant right here. So let me change this number slightly. Let me make this a 5. 3 is not large enough. Let me make this secant inverse of minus 5 over root 10. I mean, what is the angle whose secant is minus 5 over root 10? That's what we'll draw right here. Well, remember, secant is the reciprocal of cosine. So if the secant is minus 5 over root 10, then the cosine of this angle, A, is what? Minus root 10 over 5. If the secant is minus root 5 over 10, then the cosine, the reciprocal secant, is minus root 10 over 5. Now, where do I choose secant inverse from? Where do I choose cosine inverse from? I have to go back to my chart. Cosine inverse is chosen between 0 and 180. So where do I have negative cosines? In the second quadrant. Let's draw something with the x value minus root 10 and the radius 5. Root 10 is a little bit more than 3. So if I want to make this believable, maybe I could have this angle look like this. Root 10 and 5. Now I didn't write minus root 10 because that's a distance, but I can name this point minus root 10. I need to know the y value. The y value here is in positive direction, so I'm going to label this side positive number, but I also put a positive number here. How about the Pythagorean theorem? 10, when I square this and I get 25. So what do I got? Root 10 squared plus y squared is 5 squared. 10 plus y squared is 25. Y squared is 15. So y is plus or minus the square root of 15. And I choose plus the square root of 15 to put in my point because I have a positive y value in the second quadrant. I write a positive root 15 here so that my reference triangle has positive sides everywhere. Okay, so first mission, I know what A is. I know where A is. Let's do the sine inverse of 1/5. Sine inverse of 1/5, I choose the sine from first and fourth quadrants. In fact, when the value is positive, all of the inverse functions come from the first quadrant. So I need sine of 1/5. That means the y over the r is 1/5. So again, that's a very short height and a long radius. So that's a 5:1 ratio. And the Pythagorean theorem, I fill in this other side. If I square this, I get 25. If I square this, I get 1. So I need 24 more units. I need the square root of 24 here. The square root of 24 is 2√6. Just work this out with the Pythagorean theorem, but let me write it out. X squared plus 1 squared is 5 squared. X squared is 25 minus 1. X is the square root of 24 plus or minus, and 24 is 4 times 6. So X is 2√6, and I choose plus because I'm in the first quadrant. So the name of that point right there is 2√6 and 1. Okay, now I know B. This is B, sine inverse of 1/5. Now I'm going to work out the tangent of A plus B, and I can draw after I identify the tangent. You have a good feeling for where A plus B is right now anyway. Look at B, it's so slight. I am guessing that if you take A and you add B a little bit more, then you're still going to be in the second quadrant. You say, oh, maybe you could spill over into the third quadrant. Well, we'll know from the tangent, because the tangent in the second quadrant is negative, tangent in the third quadrant is positive. So I'll know based on what I get out of here, which quadrant I'm in if I want to draw this. Okay, so this is a valuable skill. Let's move this paper up. And remember, my target is cotangent, but I need to write down the tangent. So what's the tangent of this angle A and this angle B that I've just drawn? What's the formula for tan A plus B? Tan A plus tan B over 1 minus tan A times tan B. Okay, make sure the plus here matches the plus here and changes to a minus there. Now the tangent of angle A is minus y over x. That's √15 over √10 negative. Tangent of B is 1 over 2√6. Wow, this is going to be a nasty number. There's too many roots. Now, I say ordinarily I don't want to rationalize denominators, but I might got a lot of roots in here. I got to be careful. Now I'll do 1 minus. Repeat these numbers. √15 over √10 minus, so that'll turn into a plus, 1 over 2√6. Well, let's take stock of this, and then we'll decide what we have to do. Do I go for common denominators? Do I simplify things? Let's say, first, I'm just going to work my numbers together. 2√60 on the bottom. And on the top, if I got common denominators, I'd have to use 2√60 also. This is very awkward, isn't it? So let's multiply this one by √10 top and bottom. Let's multiply this one by 2 root 6, top and bottom. So I have minus 2 root 90 plus root 10 divided by 2 root 60. Now, I think that I can simplify root 60. I think I can simplify root 90, but first I just want to get people together. I can make one fraction right here and say 2 root 60 over 2 root 60. So let's write minus 2 root 90. And then if we're really brave, we're going to check it on the calculator. And then divided by 2 root 60 minus root 15 over 2 root 60. And remember, I'm just calculating tangent. I'll still have to flip it over again for cotangent. So now I invert and multiply, but that'll just cancel these 2 root 60s. So I think now's the time I could simplify this 90 root. I can't simplify 10 root. I could simplify root 60, but there's nothing to simplify in root 15. Let's think of 90 as 9 times 10. So square root of 90 is 3 root 10. So I have minus 6 root 10 here. And there's plus another root 10. That's minus 5 root 10. That's coming out nicer than I expected. Sometimes when things are too nice, you get nervous. Let's think about 60 as 4 times 15. So the square root of 60 is the square root of 15 times 4, 2 root 15. So this is 2 root 15, 4 root 15 minus 1 root 15 is 3 root 15. Then in between that, root 10 and root 15, they both share root 5. I could cancel that out and say minus 5 root 2 over 3 root 3. Now remember, that's the tangent of a plus b. I want the cotangent. So now I can write the cotangent of a plus b is 3 root 3 over 5 root 2 negative. It's going to be negative, which is good because I thought it was going to show up in the second quadrant. That's possible. Can I get rid of the 2 roots? Why do I want 2 roots in there? Let's multiply top and bottom by root 2. Minus 3 root 6 over 5 times 2, 10. If I multiply top and bottom by root 2, I only have one radical now. Can I draw this angle? Draw an angle whose cotangent is minus 3 over root 6 divided by 10. That means cotangent is what? Adjacent over opposite. So that means my opposite side is 10, and my adjacent side has a length of 3 root 6. That's about 7-ish. Ask your calculator what that is. So let's make the adjacent side 3 root 6, the opposite side 10. Now my length spacing is not excellent here. So if the cotangent, remember the tangent is 10 over 3 root 6. This is 10 over minus over 3 root 6 here. And this point is minus 10 and minus 3 root 6. What would that make the hypotenuse? 100, and if I square this, I get 9 times 6 is what, 54, 154? That means this hypotenuse is 154. And can I simplify that in any way? 2 times 77, no, 77 is 7 times 11. That does not simplify. Now, I'm a little bit nervous to even try this, but I should be able to type these angles in just like this and see if I get this number. Now, I cannot type in cotangent. I don't have a cotangent button, but I can do 1 divided by tangent. So let's try it. Now, if it fails, I'm not quite sure what I'm going to do with that, but let's try to type it in right there, because this would be like the acid test. Okay, 1 divided by tangent. Oh shoot, I don't have a secant inverse button. Well, then what do I have to do? I have to use the cosine inverse button. Instead of secant inverse minus 5 over root 10, I have to type cosine inverse, excuse me, back that up. I have to type cosine inverse of minus root 10 over 5. Square root of 10 divided by 5. Okay, so that says the same thing as secant inverse of minus 5 over root 10. Now I can add sine inverse of 1/5 plus sine inverse of 1/5 and close that parentheses. Let's divide. It's negative. That's not too bad. Negative 1.2. I'm nervous about that. And the trouble is, I cannot turn this into a fraction. So we've got to have something wrong, and you're going to have to find the error here. But see, 3 root 6, I don't think it's going to beat 10. So that this number is bigger than 1 in absolute value. That means something is not right. But just to show that, what's 3 root 6 divided by 10? I'm just kind of curious what the reciprocal of that is. And that doesn't match it either. But I can't go get the answer by fishing like that. So let's scan this carefully to see if we find where we did the mistake. Could be in the drawing, could be in the simplifying. So if you see that answer, let me know, or you can study this later and let me know. But let's just carefully look at this. Secant inverse of minus 5 over root 10. This will give me a secant, 1 over cosine of 5 over root 10. The x is negative. And 115 plus 10 is 25, which is a square of that. So this angle looks nicely drawn. Sine inverse of 1/5 was less work. Sine of 1/5 is this angle, first quadrant. This is 25, this is 1, so this square has to be 24. And 2 root 6 squared is 24. So that's 2 root 6, got it. Now I have to work out the tangent of a plus b. Something here is not quite correct. So the tangent of a plus b, I'm using this identity. And we verify the identity right here. Tangent of a plus b is tan a plus tan b over 1 minus tan A times tan B. Maybe our drawing's good, but our simplifying is bad. So the tangent of A is 15 over minus root 10. Tangent of B is 1 over 2 root 6. Put them in here and multiply. I got the common denominators. Root 10 minus 2 root 90, 2 root 60. I got common denominators downstairs. Minus 15, 2 root 60. 2 root 60 over 2 root 60. I'm checking down here. Okay, see, this could be it right here. So always pay attention to your signs. This was minus minus, right? That makes this a plus sign. So don't necessarily destroy your work now. Just carefully correct that plus sign. So that makes this a plus sign. That makes this a plus sign. That makes that 2 times 2 root 15 plus 1 times root 15. So that's 4 root 15 plus 1 root 15. That is 5 root 15. That's prettier. Then I get to cancel the 5s. And I just have root 10 over root 15 with a negative sign. That's root 2 over root 3 with a negative sign. And so root 3 over root 2 with a negative sign. And now let's get rid of the root 2 on the bottom. Minus root 6 over 2. Multiply top and bottom by root 2. Now I'm hoping, let's check this out and see if we saved it. I'm hoping that minus root 6 over 2 turns into that number. Excuse me. Wow, that's nice. I mean, you're not always able to save everything on the fly like that, but I think we found the mistake. Thankfully, we only made one mistake. Okay. So this is minus 6 over 2, so if I were to draw that carefully, tangent is 2 over root 6. Cotangent is root 6 over 2. So this will be 2 root 6. And there will be the angle A plus B. And the hypotenuse would be 4 plus 6 is 10. The hypotenuse would be root 10. This squared plus this squared, 4 plus 6 is 10. And the hypotenuse is the square root of that, root 10. The name of this point is back root 6 up to okay, now that's carefully drawn, but that was a challenge problem. That was certainly a challenge problem. Okay, last identities today. And they look like a long list of identities, but I'll show you how you can remember them. So let's go back to our paper. The trouble with this product of sum to product identities, look at this. You got 8 identities, combinations of sine and cosine to drive you crazy. So you don't memorize these. You just remember where to look for them. And then you can use them in that manner. For example, What happens if you wanted to graph? Oh, how about sine of 3x minus the sine of 5x? Now I could type this in the calculator or Desmos, no problem. But I could also try to make sense out of this drawing by referring to the sum to product identities. I'm looking for sine minus sine. So you look among the sum to product identities for sine minus sine. Oh, here's sine A minus sine B. And they say, do this. Take the 2 times the cosine of A plus B over 2 times the sine of A minus B over 2. So I'm going to use this identity. Sine of A minus sine B is 2 times the cosine of A plus B over 2 times the sine of A minus B over 2. And let's see if the graph of this matches the graph of this. Now look at A plus B over 2. That's like the average of A and B. So if A is 3x and B is 5x, then A plus B is 8x, and 8x divided by 2 is 4x. How about A minus B over 2? Be careful with your signs. If A is 3x and B is 5x, then 3 minus 5x, 3x minus 5x is negative 2x. And negative 2x divided by 2 is negative x. Now, before you go and graph this, let's think about sine of negative x. What identity do we have for sine of negative x? Back to our sheet. I've seen it somewhere. The even odd identities. And this is why I didn't like my green highlighter, so I apologize. Sine of minus theta is minus sine theta. Sine is an odd function, so the sine of minus x is equal to minus sine x. So I can replace this with minus sine x. Bring the minus sign out front. Negative 2 cos 4x times sine x. So now let's graph these two things side by side. Because the question you're interested in is what happens when you add two sine waves? And apparently the answer is you get a product of a cos wave and a sine wave. But what does that mean about the shape? Let's type that in. I'm going to open up Desmos here, and then I'll share that window with you. Share window, Desmos. Okay, so first let's graph sine 3x minus sine 5x. And that looks wiggly and weird, right? Now, notice how I didn't have to put parentheses around the 3x or the 5x. Desmos allows me to do that. If you're more comfortable typing in parentheses around that, you go right ahead. Just put them in the right place. There. And do I want to expand this? What I do notice about this is it does repeat. Do you see how it is periodic? Even though it's not at one sine or cosine wave, it does repeat itself. Let me expand it a little bit. Let's look at the period too. How long does it take to repeat itself? It repeats itself. It goes through this little small rise, small fall. Well, here it does that backwards, but then here it does it forwards. So that's about 6 and a little bit more. Maybe I should think in terms of pi. I bet that's 6 is 2 pi. Let's try the x-axis in terms of pi. Yes, that's very nice. So here is one period from 0 to 2 pi. Let me just highlight that one period. That is one period of that graph. I wouldn't draw this without a calculator, Desmo, so this is not part of our standard drawing responsibilities. But I'm curious what happens if I type in -2 cosine 4x. That's not impressive. Times sine of x. And you see it's exactly the same graph. It fits perfectly. Now maybe I could illustrate that with dotted and red. So the red thing is under here from 0 to pi. Here's the blue dotted thing right on top of it. And I want to draw one more curve on here to show you what's happening. Do you see the cosine of 4x argument? And the sine has an x argument. The 4x means what I'm experiencing are 4 cosine waves between 0 and 2 pi. But I don't see 4 cosine waves. But this sine wave is just one period. What I really have here, let me put the sine in front of the cosine. Doesn't matter which order I write that. What I really have here is a cosine wave with a funny amplitude. Think about this as a cosine wave with a funny amplitude of -2 sine x. So let me draw -2 sine x on top of this. And do you see how it fits the peaks and valleys? Let me draw 2 sine x next to it. It won't let me draw it on the same line, so I'll do it underneath. So the sine x, let me make them both green. And let me make them dotted. Do you see what the sine x is doing? This 2 sine x and -2 sine x. It's like an envelope. It's like an envelope which contains 4 cosine waves and pinches them to 0 in between there and there. And now this is not this problem, but the funny part is what would happen if I added more cosine waves? Let's turn this off. And instead of 4 cosine waves, let's put in 8 cosine waves. How about 16 cosine waves? Now that's getting a little bit too busy to look at. So I think I'm going to have to expand the x-axis a little bit. And let me get rid of the dottedness stuff because the dots are giving me a headache. So let me expand the x-axis or contract the y-axis, either way. Let's zoom out a bit on the y-axis. And what I want you to do is recognize what this picture comes from. This is a picture of a famous physical object. Now, not physical that you see, but physical that you hear. Does anybody recognize what this is? If you play a musical instrument, a stringed musical instrument. Let me pump this up to 20 cosine waves. This phenomena is called a beat. And the idea here is, let's say you're tuning a guitar or tuning a piano or a violin or a mandolin, you know, whatever you like, any stringed instrument. You're trying to make the sound of one instrument on the 5th fret, sound of one string on the 5th fret equal to the next string open. That's what you'd say on a guitar. And the problem is if the two strings are just slightly different in frequency, now what would produce an average of 20 and a difference of 2? It would be two strings that are very close in frequency, nearly 20 in frequency. Now, the frequency of guitar string, I know, you know, E, about 440 hertz. I'm not thinking about guitar strings when I talk about 20 and 1. But the idea is if you have two strings that are very close to each other in frequency, what happens when you pluck them? You hear this, when you pluck them, you hear wow, 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 wow. And then when the strings become closer in frequency, you hear the beat expand. Wow, wow, wow. I can't sing it because I can't sing to save my life. But I could have brought down a guitar, I guess. I didn't think about that ahead of time. And the idea is what? When you get rid of the wah, 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 when the strings become so close that you can't detect that beat anymore, then the two strings have the same frequency. And you've tuned that string. And then you go to the next string. Now, on a guitar, you only have 6 strings. So that's not such a big deal. You know, a little bit of practice, you tune your guitar. In the old days, people used to get paid serious money to tune pianos. And I don't have a piano, so I've never had to pay someone to tune it. And I don't know how to play the piano anyway, but let's say you had some fancy piano. Well, you can't have some fancy piano sitting in your house out of tune. You would only have the fancy piano in your house if you knew how to play it, probably. But with 88 keys, with 88 strings, do you understand the care that it would take to tune that piano? Not just so that the next string matches the string next to it, not just, but the string 60 strings later is in sync with all the other strings. So in that sense, people that tuned pianos, and you're going to have to look this up online if you like, they had extraordinarily sensitive ears. Now you could have sensitive instruments today, but it still is a lot of care to tune a piano properly. Okay, if you got a guitar, you may have heard of this idea before. You may have heard it with your ear, and now you've seen it with your eye. And this is one of the key purposes of the sum to product or product to sum identities. So you use it just as I demonstrated here. You look it up when you need to build the formula. I'll tell you the other reason you should recognize this picture, and it's a very crude picture, I admit, but I can't even say to you anymore, every one of you has one of these, an AM radio. I mean, maybe you have an AM radio, maybe you have a kitchen radio, maybe in your car you have an AM radio. I suppose you have an AM radio, but I don't know if the car receives it or brings it in off the internet. Maybe, right? What does AM stand for? Amplitude modulation. The radio signal codes information sent to your radio. The broadcast signal modulates the amplitude of the sound wave. And that's what you see right here. You see the amplitude being modulated. Now, there's a lot more to it than that, because otherwise your radio would just go wah, 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 wah. Okay. Which it might do if it's, disrepair or got heavy amount of interference. You can actually hear that sometimes in a very bad radio signal. But I don't know how many people are always using actual radio signals anymore. Okay. Think of the sum to product and product to sum identities as something in your cookbook that you pull up when you want to compare something like that. They're kind of fun and curious to make nice graphs. Let me go back to my paper. But I don't want you to memorize these, and I don't encourage you to memorize them. You could construct them from the sum and difference identities. And we could show you that later if you like. But right now, these are just identities that you look up as needed if someone asks you to use them. Okay. The weather did turn nicer, so you can actually go outside and work in your yard if you have to get rid of some leaves. I did that a little too early and got a cold, so guys, make sure you dress warm. I'm still finishing up your exams, and we'll get those back to you, and then we'll see you next week. So let me end this meeting and post these notes, and I'll see you later. You guys have a good weekend.